All right. Hello, everyone. Can I have your attention back to the class? Okay. How's everyone? Good? Good week so far? First day, right? All right. So any concern or question before we start this session? Are we good? I believe half of you probably had your first tutorial on Friday, and the rest you're going to have your tutorial today. And at 2 or 3, I guess 3, maybe I'm wrong, check your schedule. And it is on tutorial 1, okay? All right, so let's get started with today's topic. So far we said we will focus on the single degree of freedom system. We built sort of the foundation. We talk about that in vibration, we deal with the small motion, so we can approximate sine and cosine or other nonlinearities. And then we review quick things like we did a brief review or quick review from dynamics and also modeling as well. All right, let's solve one vibration problem now, and which is one of the simplest. Most likely you've seen this one before in physics. So we have a pendulum, and it's a simple pendulum. When we refer to a simple pendulum, it means the bar or the link that connect the main mat, we can neglect the mass. So this one I can write as negligible mass. Compare with the mass of m of this bob of this pendulum. Okay, we consider it a simple pendulum. So the pendulum is at equilibrium, and we like to find its natural frequency or equation of motion. Okay, so again, if you recall from the main category that we had, we said we divide vibration to free vibration and forced vibration. So this one, obviously, there is no external force. Therefore, it goes under the category of free vibrations, right? And when we deal with free vibration, the system is at equilibrium. We assume that if we disturb it a little bit from its equilibrium, then what will happen? So this one we can simply visualize it, right? If it's a pendulum, if I remove it from its, if I disturb it from its equilibrium, it's going to swing left and right, left and right. And since we are dealing with an ideal situation right now, no friction, nothing, we'll say it continues forever, right? So we like to write the equation of motion for this one. So we did the first step then. The first step was the kinematics. Figuring out how a system is going to move, which for this one is very simple. The second is draw the free body diagrams, right? Let's do that. If I disturb this system from equilibrium, then I can say this pendulum, now I'm just going to exaggerate, goes to, let's say, that position to the right. So I need to select a variable. Let's select our variable, or because of degree of freedom of this system, theta, but we can choose x. We can choose x and y and then relate them somehow. But it makes sense to go with theta because this one is a rotating system. Okay, so this is then what I will have if I disturb this system from its equilibrium. The second step is drawing the free body diagram. So what I have here is a pin at O. So a pin at O, we learned that it's going to have 2 reactions. We don't know the direction of those reactions, and it doesn't matter, because even if we are interested in finding those and we are wrong in terms of direction, we just get the negative values. So I will have OX and OY. Let's call this joint O. And we know O is a joint. This is a pin, and a pin can let the system to freely rotate. So it's just resisting X and Y. So now the important question that always we need to ask, should I include weight or not, right? And our trick was that we look at the equilibrium. So at equilibrium position, is there any spring? So luckily in this question, there is no spring. And if there was a spring, then you would ask, so is this spring being pre-tension or pre-compression because of weight? Then we don't include mass because we know eventually they're going to cancel out each other. So in this problem, we don't have any mass, any spring. So definitely there is no pre-tension or pre-compression. We have to include mass in our free body diagram, right? So I will add then the weight mg here. So that's the free body diagram. So the second step, okay? The first step then kinematics, figuring out how system moves, which it is easy, finding a variable, drawing the free body diagram, which was the second step. And then writing the equation of motion. We said always in this course and in dynamics, we have two methods, Newton methods and Lagrange equation, right? So since we are at the beginning of the course, we try to apply both methods in most of the problems, but later you will find out which method is easier, and for your exam, your assignment, your quiz, or in future, of course, you go with the method which is easier. And in the first lecture, I told you the advantage and disadvantage of each, which you're gonna find out on your own, the advantage and disadvantage of each method. So let's start with the Newton law. So, and of course, here we are dealing with a particle, right? Because m is a particle and this link doesn't have any mass. So we are dealing with a particle. So Newton laws is what we go for. Or you can assume the whole thing as a rigid body and go with the Euler law. Doesn't matter really. Let's write it by the Euler's law. Just a practice for you and consider it as more like a rigid body. Because Newton law is just the boring one, sum of the forces ma. So Euler's law. And also we don't want Eulers to get upset. Right? Eulers and Newton law, they are basically the same. Euler is just for rigid body and it has one extra equation for rotation. So the Euler's law says that after you draw the free body diagram, if the system is a rotating system about a fixed point, which is the scenario here, sum of all the moment about that point must be equal to mass moment of inertia multiplied by alpha, okay? And here we need to be careful about the sign. What is a positive direction? What is a negative direction? And the key is this coordinate that we selected, okay? The coordinate that I selected here, by showing this, I assume that rotating in this direction, which is, if I can get my mouse, okay. So which is counterclockwise, it's positive. But someone may disturb it going to the left and assuming rotating clockwise is positive. That's totally fine. But we follow what we draw here, right? I draw like theta in this direction, and this is a counterclockwise. So in order not to forget or get confused, and you better develop this habit, just put that things there so you remember that any force that rotates this system like in that direction, which is the direction of theta, is positive, and anything else, the opposite is going to be negative. Of course, for this question is easy, but there are problems that there are lots of forces and we need to be careful about the direction. So if I want to take the moment about point O, we know how to do that. We learned before, right? So taking the moment about point O, I need to draw a line along the, like the force, right? This force is along this line. And then I need to find out the perpendicular distance between like this point O and this line. Right? And this distance, I can easily figure it out. It will be, okay, let's assume the length of this pendulum is L. Should have been given by the question to us. So this one then will be L sine theta. All right. So let's take the moment about that point. It's going to be minus mg, the force, because the force tried to rotate it in the opposite direction, right? Opposite direction of theta. Minus mg, the distance, L sine theta. That's the only force that I have. Equal to, so according to Euler law, the total mass moment of inertia about 0.0. So here I have a particle, which is mass m. The question doesn't tell us that it has a radius. So if the question says that this is a sphere and it has a radius, that's a totally different story. But here, no talking about the size of this. So we assume it's a particle. And we know for a particle, the moment of inertia, mass moment of inertia, is simply the mass multiplied by the distance to that point squared. Okay, so that's IO. And then alpha. Alpha is angular velocity. Because our variable here is theta, then automatically this, we can show it by theta double dot. Okay. So this is the equation of motion. Obviously, it is nonlinear, but we had a deal at the very beginning. We said in this course, variables are very small. It goes under category of vibration, and that was the main difference between vibration and dynamics. If you go to a course like dynamics, Manu 265, for example, we assume large motion. All right, so this pendulum goes maybe 60 degrees, but here in vibration, we assume this theta is in a range of 1 degree or 2 degrees. So with that deal, we can approximate this theta and substitute it simply by theta, right? This is what we agreed. So if I simplify my equation, then I would get theta double dot plus, let's divide everything by L, theta equal to 0. This is our equation of motion. It's the second order, right? So which is familiar for us. Again, if we go back to the second session or third session, we talked about the mass and a spring. And if you remember for a mass and a spring, we had like this equation, mass spring. We had equation which was mx double dot plus kx is equal to 0. And we did a whole bunch of calculation and we find out that the natural frequency of this system is k over m. Now I can find like a similarity between these two equations of motion, right? And simply pretend that whatever coefficient I have, like over here, which is 1, and whatever coefficient I have over here, which is G over L, they represent the mass and stiffness of this system. Okay. Interesting. Okay. So again, we look at these two equations. They are differential equation. That's just math. The math doesn't care what was the physics behind it, right? We can do the same procedure as this mx double dot plus kx equal to 0 and get to omega n square root of kn. But in vibrations, what we will do instead, we look at this equation, we compare it with the original equation of mass and a spring, and then we claim that the system that we have, it has a mass of 1 and it has a stiffness of G over L. All right. So they are not necessarily mass or a stiffness. Later you will see in question that they can have any other units. That's fine. But mathematically, this is what we call them. We call this thing equivalent mass. And we call this one equivalent stiffness. All right. So in other words, we will say that if I replace this pendulum by a mass and a spring that its mass is 1, whatever unit it is, 1 unit, and its stiffness is G over L, whatever number it can be, then these two systems are equal in terms of vibration, same frequency, they vibrate in the same frequency. So with that, then I can make this conclusion that the natural frequency for our pendulum is square root of G over L, right? K over M. Because again, remember, this is for us is K and this is M. And if you are interested, and this is the unit is, of course, we talk about it, is in radian per second. But if you are interested in knowing the natural frequency in hertz, like Fn, it's going to be 1 over 2 pi omega n, which we know the relation between omega n and Fn. All right. And the unit for this one is, depends, of course, to the unit we pick for L, but let's say we are in SI unit, it's going to be hertz or cycle per second. Which again, as I said, I'm sure you've seen this question in physics before. Any question for this one? Are we good? Make sure that you understand all these things and do not be shy to ask. Because as I said at the beginning, vibration can be very complicated, mathematically can be very heavy, but I try to keep a balance. And I try to go slow, and I guarantee that you're going to master this topic if you follow this step slowly, go to the tutorial and solve the practice problems. Okay? And you're going to be successful if you like to go to the direction of vibration things, because we discuss it, all the machine vibrates, right? It's a good job opportunity. Speaking of job opportunity, I remember once for a job interview, this was the question that I was asked. And I want to know who can answer this question. Okay, everybody's here. Imagine that you are for a very important job interview, high salary, and this is a job that you want. And they put this question in front of you. They ask you that we have a pendulum like this, similar to exactly that what you see here. And this pendulum, they tell you that it has, like at the bottom, it has a ball like this one, similar exactly to this one. And the only difference is this bob or this sphere is, imagine that it is a hollow sphere. Inside is empty, it's more like a vessel, a small one. And inside it, there is water. Okay, so far it's clear. So we have this pendulum, and at the bottom, rather than having a mass particle, M, we have a bob, and inside that bob, like it is hollow, there is water. Okay, so, and then there is a hole here at the bottom, like a small hole. So, and then this thing swing, vibrate. Is the natural frequency of this system is going to stay the same over time, or no, it's going to change? But that's the question I was asked. Okay. Is it clear? So the system is the pendulum, the water is dripping, right? Slowly. And over time, we are interested to know if the natural frequency of this system is going to stay the same or is going to change. And here is the formula or everything that you learn in your vibration course. That the natural frequency is square root of G over L. You have 30 seconds to think about it, or discuss with your friend. And then if you answer correctly, you will be higher. Okay, now any volunteer, brave volunteer? Yes.
It wouldn't change because this equation would still describe it and it is dependent on that.
Okay, so sorry, I don't catch your name. Your say it again? Here. All right. So you're saying that the if we look at this formula, there is no mass, right? And we know the mass of this thing is changing, so it is independent of mass. So it's going to stay. It's going to be constant. What else? Alberto? When we talk, we can remove the mass because it's a large class, that's okay, and we can get it. Okay.
We have to assume that the slender rod is not extending due to the weight of the water and retracting as the water.
Okay, so the bar, right? You need to make sure that it's not extending. That's what you're saying. So imagine that this is rigid and it's not extending. Okay, and you go ahead.
Yeah, so you have to assume that the mass of the bar stays negligible because the sphere is empty.
Okay, let's assume that this is negligible.
Okay, so then other than that, the only thing you can would be to get your damping effects.
And no damping. Let's say your ideal. Then constant. Okay, and the guy with yellow.
So if you look at Euler's law, the equation setup, both sides of the equation mass is independent, and then
Okay.
that's what still say.
All right, so they stay constant then.
And then the mass, so in all the equation you were solved, right? If it's time dependent, you change it.
Right.
Will change in the same value on both sides.
Yeah, let's say they stay the same value because this is m coming from this m, right? And this is n. So they are going to change.
But at the
You're
same
right,
rate.
but at the same rate, yes.
So that's all time loss, and that's all stay the same.
Okay, so they are constant. All right, so for constant and what else? Go ahead.
I think we should assume the central mass. If not, we should just lump the.
Okay, center of mass, I like that. And you have the same idea?
I was just gonna say, with water drains, you keep treating it as a point mass. Because if the water drains and throws out your moment of inertia, then the equation like
Okay, yeah, I like that one. So let's see what like our friends. You're Marek, right?
Yeah.
Okay, and I don't know your name, so because we did math. So one little things that you should have paid attention here. Alberto also somehow mentioned it. Is the length. The mass is constant here, but what about this L? So L is the distance between like the center of mass and point O, right? When we had this little particle, yes, we ignore the radius, but when they ask us that inside there is water, so do you guys agree that, let's say if I have sphere that it is full of water, then the center of mass is here. But let's say over time, when the water is like dripping and coming down, we know the center of mass is gonna change, right? It becomes like come lower. Do you agree? Like when it is like halfway, then the center of mass is like close to the bottom. So this L is increasing, so it means the natural frequency is decreasing. Okay. Do you guys agree? Okay. So it means over time, it's gonna move slower or faster. You just said Fn is gonna decrease, right? Because L increase. If Fn is gonna decrease, it means less number of cycles per second. It's gonna be slower, right? Decrease. Yeah, it's gonna be slow. Yeah. Okay, so thank you, and let's get rid of that one. It was just The interview question. Let's solve the same problem with Lagrange equation. Did you guys have Lagrange equation in other courses or no? No? No other courses? Okay. So the Lagrange equations, if again you recall, we said you need to calculate T, which is kinetic energy. And you need to calculate U, which is potential energy. Right? T and U, you calculate T and U. And Lagrange equation has a very long form, which we will get to that, but in a simple form, like simple form, it is d over dt derivative of t with respect to like our variable, which is here theta dot plus derivative of u with respect to theta equal to 0. And the variable can be x, can be theta, and can be anything. Or we can have several variables, which is the later things. So for this system, we know how to calculate T and U, right? T, the kinetic energy. Again, we have a system which is pinned to the ground. It's rotate about a certain point. Last lecture, we talked about 3 scenarios. Let me move back quickly, right? Here. Kinetic energy. When something is just translating, right? A box that can just move. When something is fixed to the ground and rotate, and when something is float, both rotate and translate. And we have a formula for each of them. All right. So, and by the way, some ask question, apparently they got confused. When we have a disk like this one, where we claim that it rolls without any slippage. It rolls without any slippage. So we can write this relation, and we can claim that it goes under category of like this fixed point for a moment, and then we write the rest. So anyway, for when something is fixed, the kinetic energy is simply half of I/O omega squared. So moving here, then I can write down T to be half of I/O omega squared, which is half of m L squared theta dot squared. That's T, right? U is easy. I don't have any spring. So in this course, we said we have 2 potential energies or 2 types. One is gravitational, and another is coming from springs, like elastic energy, which in this case, no spring. So only things that I have is mg delta H. So from equilibrium, the mass of this system moves up. So it is positive mg. How much moved up? If I figure out these triangle things, it's going to be L 1 minus cosine theta, right? So delta H is like the center of mass moved this amount, which from the geometry, you can figure it out. So I have T and U, right? So we said we can replace sine and cosine, but we had one sort of something to pay attention, that if we need to take derivatives, we always substitute sine and cosine at the very end when we take all the derivatives. Otherwise, we're just going to get zeros. So let's take the derivative, and then we will be worried about the sine and cosine at that point. So derivative of t with respect to theta dot, it's going to be ml squared, which is a constant, right? And theta dot power 2, which cancel out by 1.5, so it gives me 1 over theta dot. Okay. So keep in mind, don't get confused. We are taking derivative with respect to the variable that has that shape, theta dot. Not with time, not with theta dot, right? Like if in this equation I had an extra things, for example, let's assume 2 theta. Okay, the derivative of this thing, this t with respect to theta dot, still would be the same, right? Because this is theta, it's not theta dot, and we are taking derivative with respect to theta dot. We will see problems like that soon. So you will get it, and it's easy. So I have that things. Now let's take the derivative of everything that I got here with respect to time. Okay, so this is that part inside the bracket. Now, if I take the derivative of everything here with respect to time, I would get ml squared. Derivative of theta dot with respect to time, this gives me theta dot. The other one is easy. Derivative of u with respect to theta. So it will be mgl is a constant. Derivative of 1 is 0. Derivative of cosine is sine theta. Because it's a negative, it's going to be positive or something. Again, do not get confused. We do not take the derivative with respect to time here, right? We don't have any theta dot. We are taking the derivative of cosine theta with respect to theta. So put them together. I would have ml squared theta double dot plus mgl sine theta equal to 0. Now I'm allowed to replace sine theta with theta, simplify everything. So we will get the same result. So the good things about the Lagrange equation is no free body diagram. We don't need to be worry about the forces, direction, or anything, get confused. But it has derivatives, which is not really a big deal. In some problems, this method is easier. In some problems, the Euler's or Newton law is easier. Depends on the problem. And I put a lot of practice problems for you. So to practice both methods, so it's going to be a second nature for you making derivatives and solving problems. Okay. Any question that you like me to go over, review, anything? We're good? Okay. So in that case, do the same things for a compound pendulum. Let's in this class, let's use, for example, Newton law here or Euler's law. The first method. You have a minute to write it down, and then I will write so you could compare your solution. This is a compound pendulum. Compound pendulum, now the link has a mass. So let's assume the length of this thing is L, and let's say the mass is M, and let's say it is a uniform, a slender bar, and its center of gravity is like exactly in the middle, and let's call it G. Try to do these 3 steps, how this system is moving, the kinematics, which you know, right? It's a pendulum. Then free body diagram, and then the Euler's law. These 3 steps, try to find the equations. Okay, probably wherever you are, I'm sure you are on the right track, but let's quickly solve it together and move on to the next example of section. So system, we know how it moves, the free body diagram, because I have the center of mass, it simply is an mg. Definitely we need to include weight because there is no spring here. And O is a fixed point, so we don't need to be worried about that, but just to include it in the free body diagram, I have the OX and OY. So if I simply take the moment about point O, because it's a rigid body, it has a moment of inertia, I take the moment about point O, it is IO alpha. So similarly, our positive direction was counterclockwise. So this is a positive direction. So I would get minus mg multiplied by the distance, which is half of L sine theta, right? This distance. So this guy is half of L, and this angle is theta. So simply this distance will be half of L sine theta. And it is negative because it tried to rotate it in the opposite direction of theta. No other force. IO for a link, if again remember from last day, we said the mass moment of inertia for few things. One was a bar, another one was a disk, and then a cube or a box. Those things you should remember them. For a link about 1 point, one of its end was, who remembers? 1/3, exactly. 1/3 m L2, and alpha is theta double. Okay. So I just write it down for those who forget. So for a bar, for a slender bar, I bar is equal to 1/12 ml squared. And if we just use the law of parallel access, I about O is I bar plus m half of L distance, which gives us 1/3 ml squared. And we are done. So simplify things and get things ordered. What do I get here? Theta double dot plus 3G2L theta equal to 0. So my natural frequency will be 3G2L. Okay. Please try this one on your own with the Lagrange equation as well. You just need to find T, find U, and then take the derivative of T with respect to theta dot, take the derivative of these things with respect to time, take the derivative of U with respect to theta, right? And then put all of them together. So, and then, yeah, and the rest. Because Lagrange equation, we are looking after finding if you check your textbook or somewhere else, you saw Lagrange equation. It is a long equation. This is a short form. It has three other elements, which we will add them later. When we add friction, when we add other things like external forces. For now, the simple case. Okay, so let's solve one example which is different than pendulum, and let's use the Euler's law for this one. Again, spend a minute, try to think about it. Three simple steps. First, how this thing is going to move, like the kinematics, then free body diagrams, and then simply the equation of motion. And as the system said, hopefully somewhere, this is an equilibrium. So usually what you see here is the equilibrium condition. For those who arrived late, don't forget, today is your tutorial. If you didn't attend the Friday session. So Mondays is repeat of Fridays with the same TA, with the same like question. And today is on tutorial 1, and tutorial 1 questions are at the end of your like lecture note. Some of the TAs may solve extra problems than those on the, depends on the time of day. And also, if you guys have any question, like after class, if you could stay like outside this door, not outside that door, but over here, which is there is a lot of them outside these things. Because usually the next teacher comes and they expect me to leave here. So if you have a question, I have a lot of time after the lecture, and I will stay outside and answer a question. If you have more question later, I said it in on the canvas. Do not be shy. Send me an email. I'm available for office hours. If you then don't email me or don't ask question, I feel like you are good. Okay. So any question after the class? I'm free after the class, so I can stay outside even for an hour. That's fine. So stay outside this door. And if any other question later when you solve the problem, you can either ask by email if it's a quick question, or if you need office hour, I'm happy to send you an email. We'll find the time to meet in my office, and then, yeah. Okay, so let's get these things done. We have 3 minutes. So we have a system at equilibrium. So the question didn't say it here, but usually clearly says, oh, it says it is at rest in the horizontal position as shown. So that's the equilibrium, right? So this is a free vibration, no external load. The system is at equilibrium. Everything is static. So we come and disturb this system. Okay, we disturb it a little bit and it starts moving. We want to see if we disturb this system somehow, what is its natural frequency? To do so, we need to find the equation of motion. And all of these things you may ask now, who cares about the natural frequency of this system? But it will make sense as we go further and further. For this section, our focus is natural frequency and the equation of motion. Okay, so this is at equilibrium. I disturb it. I assume that I disturb it a little bit down, but it's totally fine if somebody says I like to disturb it up. That's totally fine. It's just the matter of how you show it and the variable you choose. So theta, this direction, this is what I picked. But it's totally up to you if you say that I push it up. So theta going counterclockwise. You can try, and then the equation will be exactly the same. Second, draw the free body diagram, and you need to always ask this question: should I add or consider weight or not in free body diagram? So in this problem, the trick is, as I said before, remove the springs. Is this system is going to stay at equilibrium? No, right? So it means that this is because of the spring that these systems stay at equilibrium. Therefore, this weight has been canceled out by some sort of pretension and compression in these springs. So since there is pretension and compression in these springs, right, I don't consider the weight and I don't consider those pretension and compression. There is no issue if you consider them, but it's just going to be a long solution, similar to the very first problem that we solved. So here, I don't show the weight. So the only forces that I have is this spring then, right? This spring is going to apply load. And this load, because the spring being compressed, it resists the motion from what I show here. And it is K multiplied by the deflection of the spring. Because, again, we are in vibration, we can assume this deflection is very small, and therefore the deflection of a spring is simply B theta. Okay, so B theta, or you can write the triangle and then replace the sine theta by theta. That gives you exactly the same, but you can assume since it is very small, then the deflection of a spring is simply B theta. What about the spring at the top here? So it resists the motion, it is upward, and because it becomes a stretch, right? And the force is K multiplied by the deflection, which is 2B theta. I don't care about the weight because we talk about it. And then O is simply is a pin which has OX and OY. The Euler law tells us that sum of the forces about point O must be IO alpha. So if I assume that this is a positive direction, right? Clockwise is a positive direction, then I have to write KB squared theta minus 4KB squared theta. Write it down, I just write the final things. And then IO is M 3B squared theta double dot. If I simplify this one, I would get 9M theta double dot plus 5K theta is equal to 0. Okay, and in this problem now it is our mass and this is our stiffness. And we learn how to find the natural frequency, which is, okay. You have to stop here because of next class, but I will go over it again. But take a look, please. And if you have time until Wednesday, solve example 5, which is very similar to this one, but a little bit different.